Yeah, basically what I'm going to cover in 9.1, hopefully will be sufficient. Uh, if you want to read more in depth,
Yeah, found my chapter and
you
text.
can do that.
Thank you.
Okay, we'll start in a couple of minutes. Okay, today we'll spend more time in section 8.3 on moments and center of mass. If there's time left, we'll start in the section 9.3. So last time we were looking at moments of regions with uniform density. So suppose we have some function y equals f of x on the interval from a to b, and then if we select a subinterval, x sub I minus 1 to x sub I, and if we use the midpoint of that subinterval, which is x sub I bar, because x sub I bar is the correct notation or the conventional notation for the average value of the endpoints, x sub I minus 1 plus x sub I divided by 2. And so we use that to determine the height of the approximating rectangle. So we have this rectangle and the height of the rectangle corresponds to this point that's on the graph of the function. So this ordered pair is x sub I bar f of x sub I bar. And the centroid, or the center of mass of that rectangle, the x-coordinate is x sub I bar, and the y-coordinate is 1/2 f of x sub I bar. So if we refer to that rectangle on the interval from x sub I minus 1 to x sub I as the rectangle r sub I, then what we found yesterday, the moment of the rectangle r sub I about the y-axis is equal to the mass of the rectangle, which is rho times the area. The area is f of x sub I bar times delta x. and then multiplied by the horizontal distance from the center point to the y-axis, which is what x sub I bar is. And then if we rearrange the terms to be more conventional, we can write it as rho times x sub I bar times f of x sub I bar times delta x. And we get one of these expressions for each of the n rectangles that occur between x equals a and x equals b. And then if we take the limit of the sum, then the moment of the entire region that's below f of x on the interval from a to b about the y-axis is rho times the definite integral from a to b of x times f of x dx. The mass, the entire mass of the region is rho times the area of the region, and the area of the region below y equals f of x from a to b is just the definite integral of f of x dx times rho. And so the x coordinate of the center of mass, which we call x bar, that's equal to the moment about the region, or the moment of the region about the y-axis divided by the total mass. So we're going to divide this definite integral by this one. The rows cancel each other out, so we'll just write it without the row constants. So in the numerator, we have the definite integral from a to b of x times f of x dx, and then divided by the mass without the row, since those cancel. So in the denominator, we just have the area of that region. Okay, that's what we did yesterday, and then today we'll find the y-coordinate of the center of mass using the same reasoning. So the moment of the region, or I'll just start with the rectangle r sub I again. The moment of the rectangle r sub I about the x-axis is going to be the mass of the rectangle, which is the same as it was beforehand. So the mass of the rectangle is rho times the area, f of x sub I bar times delta x, multiplied by the vertical distance from the center of the rectangle to the x-axis. And the vertical distance is 1/2 f of x sub I bar. And then if we rearrange the terms to be a little more conventional, we write rho times 1/2. And notice we're multiplying f of x sub I bar by f of x sub I bar, so that's just f of x sub I bar squared, and then delta x. Okay, we get one of those for each of the n rectangles, so when we add those n terms, we get an approximation of the moment of the entire region about the x-axis. And then if we take a limit by letting n go to infinity, then the moment of the region bounded by the graph of y equals f of x and the x-axis from a to b, that's going to be the definite integral, rho times the definite integral from a to b of 1/2 times f of x squared dx. Okay, and we already found the expression for the mass of the entire region. And so the y-coordinate of the center of mass, y bar, is the moment of the region about the x-axis divided by the mass. So in the numerator, we'll write rho, I guess, one more time. Rho times the definite integral from a to b of 1/2 times f of x squared dx divided by the mass of the entire region, which is rho times the area. And then the rows cancel each other out. So we can just find the y-coordinate of the center of mass by dividing this definite integral by this one. I guess I can go ahead and write it. It's after the rows cancel, we get the definite integral from a to b of 1/2 times f of x squared dx divided by the area of the region, the definite integral of f of x from a to b. Okay, so those are pretty easy formulas for the center of mass to memorize. They're not too bad. So go ahead and memorize those. Or if you don't want to memorize it, you can always derive it the way that we did it. Okay, on the next page, we'll just summarize the things that we found. So if you're online and wondering why I'm arranging the page the way it is, it's because in the classroom, the projector is off kilter again. So anyway, let R be the region in the xy plane with uniform density rho between the graph of y equals f of x, the x-axis, and the vertical lines x equals a and x equals b. Then we'll just write down the formulas. The moment of that region R about the y-axis is capital M sub y, and this is rho times the definite integral from a to b of x times f of x dx. The moment of the region R about the x-axis is capital M sub x. This is rho times the definite integral from a to b of 1/2 times f of x squared dx. And the mass of the region R is rho times the area of the region R. So this is rho times the definite integral from a to b of f of x dx. Okay, then the location of the centroid of the region R is the ordered pair x bar, y bar. And x bar is the moment of the region R about the y-axis divided by the total mass. And we'll write it down after the rows, row divided by row cancels. So this one will be in the numerator, the definite integral from a to b of x times f of x dx. And in the denominator, the definite integral from a to b of f of x dx. And the y-coordinate of the centroid is the moment of the region R about the x-axis divided by the mass. So this one we get the definite integral from a to b of 1/2 times f of x squared dx divided by the area of that region, which is the definite integral from a to b of f of x dx. Okay, so that's all there is to it. So we'll do a couple of practice problems. On this one, find the location of the centroid of the region bounded by y equals 2x, y equals 0, and x equals 2. So I might need more space than I have here, but we'll just do a little sketch of the region. So y equals 2x. Straight line with a slope of 2 passing through the origin. And the line x equals 2 is the vertical line. So we want to find the centroid of this region. Okay, so the moment of that region about the y-axis, let's just assume that rho equals 1, so I don't have to write rho every time. Or you can just think rho times, let's see, the definite integral will be from x equals 0 to 2. And the integrand is x times f of x. Or f of x is y equals 2x. So 2x times x is 2x squared. So this is a fairly simple integral to evaluate. So we're going to get 2/3 x to the third from 0 to 2. And 2 to the third is 8. 2/3 times 8 is 16/3. So the mass is rho. So assume rho is 1. So the mass is rho times the area of that region. Since that's just a triangle, you can find the area easily enough. But we might as well just use the definite integral from 0 to 2 of 2x dx. So x squared from 0 to 2 is 4. So we use those two quantities to find the x coordinate of the centroid, center of mass. So 16 thirds divided by 4, or 16 thirds times the reciprocal of 4, which is 1/4. And then 16 thirds times 1/4 is 4 thirds. Okay, so at least the number I came up with is in that region. Well, it's on the x-axis, but at least it's between 0 and 2, so that's could be a good sign that we're on the right track. Okay, now let's find the moment of that region about the x-axis. So it's rho times the definite integral from 0 to 2 of 1/2 times the square of f of x. So our f of x is y equals 2x. So when we square 2x, we get 4x squared. Okay, so in the next step, we'll simplify 1/2 times 4, and then find the antiderivative of x to the second. So we're going to get 2 times x to the third over 2, evaluated from 0 to 2. So let's see, did something go wrong? Anyway, I get 8. So if I did that correctly, then y bar should be the moment about the x-axis divided by the mass, which is 8, divided by the area is 4. So I get 2, but
Times 3 divided by 3.
oh yeah. Yeah, that's right. So yeah, x to the third over 3 is the antiderivative. So this becomes 16 thirds instead. So yeah, y bar is 16 thirds divided by 4, which is also 4 thirds. Okay, so the centroid is the ordered pair 4 thirds, 4 thirds. So about right there. So I'll just reiterate what we found. X bar, y bar is the ordered pair 4 thirds for x bar and 4 thirds for y bar. Yeah, watch out for those mistakes that I make. Okay, let's look at the next example. Find the location of the centroid of the region bounded by y equals sine of x, y equals 0 for values of x between 0 and pi. So if we sketch this, that might help a little bit. So from 0 to pi, and sine of pi over 2 is 1, so the graph of sine of x on that interval looks something like that. Okay, so the moment of that region about the y-axis is rho times the integral from 0 to pi of x times f of x, or f of x is sine of x, so we have x times sine of x dx. So we get to review a little bit about how to integrate by parts, and also involving a trig function. So on the side over here, let's just do what we would do if we wanted to find an antiderivative of x times sine of x using integration by parts. So if we pick u to be x and dv to be sine of x dx, sine of x dx. So du is dx, and v is negative cosine of x. So u times v is x times negative cosine of x, so we'll write it as negative x cosine of x. And then minus the integral of v du, so since v is negative cosine of x, we're subtracting a negative, so we'll write it as plus the integral of cosine of x dx. And so we get negative x cosine of x plus sine of x. Okay, so the moment of the region about the y-axis is rho times this antiderivative evaluated from 0 to pi. So negative x cosine of x plus sine of x evaluated from 0 to pi. Okay, so when x is pi, we get negative pi times cosine of pi plus sine of pi and then when x is 0, this term is going to be 0 because x is 0. And sine of 0 is also 0. Sine of pi is 0. Cosine of pi is negative 1, so the moment of the region about the y-axis is rho times pi. Okay, let's go ahead and find the moment of the region about the x-axis, and then after we found that, we'll find the the mass of the region and find the location of the centroid. Okay, so the moment of the region about the x-axis is rho times the definite integral from 0 to pi of 1/2 times f of x squared, or f of x is sine of x, so when we square sine of x, we get sine of x squared. Okay, the identity for sine of x squared that I'm going to use is the 1/2 times the quantity 1 minus cosine of 2x. Do you remember that one? So I guess I'll write a little bit more detail. I'm going to bring this factor 1/2 out front and write it as rho over 2. And then sine of x squared is 1/2 times the quantity 1 minus cosine of 2x. Okay, so in the next part, I'll multiply rho divided by 2 times 1/2. So we get rho divided by 4. And then an antiderivative of 1 minus cosine of 2x is x minus 1/2 sine of 2x. And then we're going to evaluate that from 0 to pi. So rho over 4. And when x is pi, we get pi minus, well, when x is pi, sine of 2 pi is 0. So it's pi minus 0. And then when x is 0, we get another contribution of 0. So this is going to give us rho times pi over 4. Yeah, that is the moment of that region about the x-axis. Okay, so now we find the mass of that region, which is just rho times the area. And the area is the definite integral from 0 to pi of sine of x. Okay, an antiderivative of sine of x is negative cosine of x. So this is rho times negative cosine of x evaluated from 0 to pi. So rho times negative cosine of pi minus negative cosine of 0. Cosine of pi is -1, so the negative of -1 is 1. And we're subtracting a negative, so we're going to add the cosine of 0, which is also 1. And so we get 2 times rho. Hey, now we can write down the x-coordinate of the centroid, x bar. That's the moment of the region about the y-axis divided by the mass. So we're going to get rho times pi divided by 2 times rho. The rho's cancel, so x bar is pi over 2. y bar is the moment of the region about the x-axis divided by the mass. And we found that the moment about the x-axis is rho times pi divided by 4. And we're dividing that by the mass, which is 2 times rho. So the rho's cancel, and we're left with pi divided by 8. Okay, so to summarize, x bar, y bar, the centroid, center of mass, pi over 2 for x, pi over 8 for y. So we can know ahead of time, in this case, that the x-coordinate of the centroid is pi over 2. So why would we know that just before we did any calculation? Yeah.
Because there's a line of symmetry on x equals pi over 2, which means that by definition the centroid would have to fall on that line.
Yeah, so the answer is we have a vertical line of symmetry through x equals pi over 2. So the centroid has to be on that vertical line, which is what we found. And then pi over 8, that's a little bit bigger than, it's about 0.38 about. So it's not quite halfway between the x-axis and the top of the sinusoid there. Okay, the next part involves finding the centroid of a region that's bounded by 2 curves. Okay, so if a region R with uniform density rho is bounded between 2 curves, y equals f of x and y equals g of x, where f of x is greater than or equal to g of x for values of x between a and b, then the centroid of R is x bar y bar. So as usual, x bar is the moment of the region about the y-axis divided by the mass. And to find the moment of the region about the y-axis, we multiply rho times the definite integral from a to b of x times the difference f of x minus g of x. Okay, so this is what we would expect. The new function is f of x minus g of x, right? So it's x times f of x minus g of x. And then the mass is just the rho times the area of that region. So the area of the region bounded by f of x and g of x, if f of x is greater than or equal to g of x. The area is just the definite integral from a to b of f of x minus g of x. So that's what we expect. So it's a little more tricky to find the moment of the region about the x-axis. So it's still rho times the definite integral from a to b of 1/2. But notice this might be, it's easy to overlook what's going on here. We have to square f of x and then square g of x and then find the difference. So in other words, it's not the quantity f of x minus g of x squared. which is an easy thing, an easy mistake to make if you're not careful. So we have to square f of x, square g of x, and then find the difference. So it makes sense in every way, but you can think of it graphically. If you were to square f of x minus g of x, you would be actually finding the y-coordinate of the centroid of a different region. Anyway, just watch out for that. Okay, so to summarize this, the x-coordinate of the centroid is the moment about the y-axis divided by the mass. So the rows cancel. So this is just practice writing down the formulas. So the definite integral from a to b of x times the quantity f of x minus g of x dx divided by the area of the region, because the rows cancel, which is the definite integral from a to b of f of x minus g of x. And the y-coordinate of the centroid. So the rows cancel again, so we get the definite integral from a to b of 1/2 times the quantity f of x squared minus g of x squared dx divided by the area of the region, definite integral from a to b of f of x minus g of x dx. Okay, we'll see how we do on the next example. So in this one, find the centroid of the region bounded by y equals x plus 2 and y equals x squared. So we have two functions. One is our g of x and one is our f of x. And there's nothing said about the interval that we're going to compute definite integrals over. So this one's simple enough that we can just sketch a graph of both functions and we can answer those questions. So x plus 2 graph of y equals x plus 2 has slope 1 and a y-intercept at 0, 2. And the graph of y equals x squared, that's a parabola, so it has its vertex at the origin. And the two graphs intersect at negative 1, 1. And they also intersect at the ordered pair 2, 4. So the parabola looks something like this. And so our bounded region is between x equals negative 1 and x equals 2. You can determine this algebraically, you can set the two functions equal to each other and solve the resulting quadratic equation for x, right? If you solve the equation that you get by setting x plus 2 equal to x squared, you'll get x equals -1 and x equals +2 for the solutions. That tells you the x values where the graphs intersect. Hey, but this was simple enough that we can just do it algebraically. And on that interval we can do it graphically. So on the interval from -1 to 2, the graph of y equals x plus 2 is above the graph of y equals x squared. So when we find the moment of that region about the y-axis, so for this one, I'll just omit rho, assume rho is 1, for example. So we have a definite integral from -1 to 2, and we're going to multiply x times f of x minus g of x. So we'll just note that our integrand is x plus 2 minus x squared. This is our f of x minus g of x. See what I mean? So we're going to multiply this by x, so our integrand becomes x squared plus 2x minus x to the third. Okay, so this one is fairly simple to evaluate. So an antiderivative of x squared is x to the third over 3. Antiderivative of 2x is x squared. And then an antiderivative of x to the third is x to the fourth over 4. And we evaluate this from -1 to 2. Okay, I'll leave the rest of that for you to do. I want to get to the moment of the region about the x-axis. So this one, we have to be a little bit more careful. So this is the definite integral from -1 to 2 of 1/2 times the quantity. And so I'll write it out. Our f of x is x plus 2. So we have to square that, x plus 2 squared. And then we're subtracting the square of the other function. So if you get it set up correctly, then it's not too bad after that. So 1/2 times this quantity. When we square x plus 2, we get x squared plus 4x plus 4. And then we're going to subtract x squared squared, which is minus x to the fourth. And this is also a fairly straightforward definite integral to evaluate because we just have polynomials. And then m is rho times the area. So we're omitting rho, but the area of that region is the definite integral from -1 to 2 of x plus 2 minus x squared. Hey, there's just a couple of minutes left. we can perhaps at least get started on this last example. So on this one, find the centroid of the region bounded by y equals the square root of x and y equals 1/2 x. So on the interval from 1 to 4, the graphs of those two functions intersect. So the square root of x looks something like that. It's a half of a parabola. And 1/2 x looks like this. So we have this tiny region here that we want to find the centroid of. Okay, so I'm down to a few seconds. The moment of that region about the y-axis, let's throw in rho this time. Rho times the definite integral from 0 to 4. The two graphs intersect at x equals 0 and 4. And then it's going to be x times the quantity square root of x minus 1/2 x. Or we can write it as x times the square root of x minus 1/2 x squared. And then you can replace the square root of x with x to the 1/2. So this term becomes x to the 3/2. And then after that, it's a fairly simple integral to evaluate. And we're out of time. So these problems are not too bad. There's just quite a few opportunities to make little mistakes. So just be careful with that. Okay, so tomorrow we'll start chapter 9 material. So I was going to mention this room has a capacity of 15 people, I think. And so if you're among those who attend every other day, there's room for you to attend every day because we never have half the capacity that we're allowed. So I'm just leaving that up to you if you want to attend every day. Yeah, you attend every other day, right? And so do you. If you want to attend every day, you can, because there's room. Yep. Some people already do attend every day. We made those arrangements earlier, but